In this tutorial, I will show you how to use the AnimatLab Robotics Framework to interface the control of a real robot arm with a simulation of that arm. This is the first of a series of tutorials that describe how to use the AnimatLab Robotics Framework. AnimatLab is a neuromechanical simulation system that allows you to build the body of a living organism or a mechanical system within a physically realistic virtual environment, and then build a biologically realistic neural network to control its behavior. I also plan to add other means of controlling robots for those that aren't interested in neurorobotics, but that will be the focus of another series of tutorials. These tutorials will be focused on neural control systems. The Robotics plugin allows you to build your simulation within the virtual world and get your neural network to produce the type of behavior that you want, and then, without any programming necessary, you can download the exact neural network to the actual robot and have it control the real thing. The Robotics Framework does this by looking at how your simulation is set up and then translating the movement commands that would drive the simulation into corresponding commands for the real system, and vice versa for inputs from the world to the nervous system. The primary goal of the Robotics Framework is to make it very easy for anyone to be able to build a biomimetic robot. For this first tutorial, I'll be using a simulation that I've already built. You can download the base simulation I'm starting with from the Animat Simulation Warehouse. Go to the warehouse and then search for ARM base. You'll see the robot arm base simulation. You'll need to be logged in to be able to actually download it. Once you've downloaded it, unzip it and then load the project file. Here is a side-by-side comparison of the real robot and the simulated one. The basic simulation is a 3 degree of freedom robot arm. It's pretty limited in its mobility since I wanted to keep this as simple as possible, but yet still have something interesting enough to show how it works. The first joint, the thorax coxa joint, will promote and remote an arm along the horizontal plane. The second joint, the femur tibia, will elevate and depress the arm, while the final joint will be a gripper or a pincher that will be used to grab objects. The gripper also has a contact sensor on it that detects when it's gripping an object. Each part has a Dynamix object composed of a standard geometric shape. In this case, a box. It also has a graphical mesh so that it looks like the real thing. All the parts we will be using to build the robot are from commercial, off-the-shelf robotics component. For the frame, I'm using standard Bioloid frame kit. The motors are Dynamixel AX-12 Servo motors. The gripper was a kit purchased from Robotics. The pressure sensor we'll be using was also purchased from there. In this tutorial, we'll be using an Arbotix Arduino board to control the movement of the arm and get input from the contact sensor. The Arbotix is a special Arduino board available from Robotics that allows you to control Dynamixel servo motors. Dynamixel servos are some of the most widely used servos in robotics. They have a number of benefits over standard servos. The first is that they're networked, so you can connect all of your servos up in a daisy chain and connect one to the other. This means you don't have to run numerous long wires from every servo to your control board. It also means that you can talk back and forth with the servo. On a standard servo, you specify the target position using a pulse width modulation signal, but you get no feedback from it. Dynamixel servos are much more functional than that. They give you the ability to set a target position and a target velocity. You can set the angle limits, maximum torque, and a number of other key parameters for the motor. Even more importantly though, you can also query the motor to get back important data like its current actual position and speed, and its load, and whether any errors have occurred. This allows you to have a real sensor-motor feedback loop. There's a complete part list for the robot given on the page associated with this movie, if you'd like to try and build this for yourself. All of the masses, part dimensions, speeds, and torques for this simulation are based on the real parts shown in that list. Also, if you'd like to build other types of robots using the Bioloid Frame Kit and Dynamixel Servos, then I've built a library of meshes for all of the major Bioloid parts in the comprehensive kit. You can download this from the Animat warehouse by searching for Bioloid. Each part has a low polygon version and a CAD version. I created most of the low polygon versions from detailed CAD mesh files. I suggest that you use the low poly versions in your simulations because they'll run much faster. The CAD versions are more for things like 3D printers. The base simulation we'll be starting with has the mechanical components set up and ready to go, but it doesn't have any of the control systems defined for it. For this first tutorial, we'll keep it simple and essentially hard code the arm movements to show you how the various motor control systems work. After that, we'll add a remote control to allow a user to control the arm at will. Let's start by making the simulation do something. Add 4 joints into our neural subsystem and hook them up to the 4 joints in the arm. Start with the TC and CF and finally the left and right gripper joints. Now add 2 tonic firing neurons and name them TC and CF. Then draw connections from each tonic neuron to the corresponding joint. When you connect neural and physical components, or different types of neural components, an adapter is added between them. Adapters translate signals from one system into values that are usable by another system. They're basically just converters. You can pick the source data type and the target data type. And specify a gain equation to convert the source value into a target value. This produces a generic way for different systems to talk to one another. In our tonic neurons, let's set the IH parameter to 5 nanoamps for each of them. Five nanoamps will produce a membrane voltage that will result in half activation of those neurons. We'll initially be controlling the motors using velocity control. As we change the firing rate of the neurons above or below this half activation level, we want to set positive or negative velocities. Now change the CM parameter to 1 nanofarad. This decreases the capacitance of the neuron membranes and will allow them to respond more quickly to changing inputs. Now select the TC adapter and edit its gain. Set C to be 2. And D to be -1. This will convert any firing frequencies above 0.5 to be positive velocities, and those below to negative velocities. Let's do the same thing for the other adapter. Now run the simulation and see what happens. What we'd like to happen is that the arm stays steady and doesn't move since it's not getting any stimuli to move. However, it takes a small amount of time for the tonic neurons to stabilize to their half activation state. This causes an initial hiccup in the arm. We can use a new feature in AnimatLab to eliminate this problem. Adapters now have a new parameter called Init IO Disable Duration. This allows us to specify a time window for when the simulation starts, where I/O will be turned off for this adapter. So essentially, the motor will not receive any movement commands until after this time window expires at the beginning of the simulation. This allows various neurons within the simulation to stabilize. To get over the initialization problem, I'm going to set each of the motor adapters to have an Init IO Disable Duration to 250 milliseconds. Now let's run the simulation again. This time you can see that it no longer jitters at the beginning of the simulation. Now let's add some stimuli to move the arm. We'll add a current stimulus to the TC neuron. Change the name to be TC over. Set the current to be 5 nanoamps. And the time from 0.4 to 2.2 seconds. Now add a tonic current stimulus to the CF joint. Set its name to be CF down. The current to be -5 nanoamps. And the time from 2.2 to 2.47 seconds. Now we want to add the controller for the grip. However, we're going to do it slightly differently. I would like to have one neuron for closing the grip and one for opening. Splitting it out this way will give us the ability to stop the grip once it comes into contact with an object. Let's add 2 regular firing rate neurons and change their name to grip close and grip open. change their capacitance to 1 nanofarad. And then for each of them, draw connections to both the left and right grips. For each of the adapters for the grip closed, set the C parameter of the adapter gain to be 1. For each of the adapters for the grip open, let's set the C parameter of the adapter gain to be -1. So essentially what this is doing, when you want to close the grip, it's going to have a positive velocity which will make the grip go in, and when you open the grip it'll have a negative velocity which will make it go out, and it will do this for each one of the grippers. Now let's set the Init IO disabled param to 250 milliseconds for each of them. Next, let's add a current stimulus to the grip and name it grip closed. Set the current to be 2 nanoamps and the time to be from 2.47 to 2.7 seconds. Now let's run the simulation. Okay, so our gripper arm goes over and then down and then grips onto the ball. Now let's try and pick the ball up and move it back to the bin and drop it in. Add a new current stimulus to the CF joint and name it CF up. Let's set the current to be 5 nanoamps. Time from 2.7 to 2.97 seconds. Then add another current stimulus to TC and name it TC return. Set it to be -5 nanoamps from 3 to 4.65 seconds. Now we just need to open the grip and drop the ball. Let's add a current stimulus to grip open and set its current to be 5 nanoamps from 4.9 to 5.2 seconds. Then let's run the simulation again. Uh-oh. This time when we run the simulation, the arm makes the movements that we want, but when it tries to pick the ball up, it's not able to keep a grip on it. This actually demonstrates a major problem that I ran into when trying to get the gripper to work in the simulation. No matter how hard I had it squeeze on an object, or how high I turned up the friction, the item it was gripping would just slowly slip out of the grippers. In order to get similar behavior between the simulation and the real system, I had to add a type of a cheat into the simulation. So I added a functionality for sticky parts. A sticky part is a contact sensor that can be set to stick to any other part that it comes into contact with. There's a sticky part flag on contact sensors. When you set this to true, then the part looks at a sticky on setting. If the sticky on is true, then when the contact sensor hits another part, it will stick to it. Internally, it's creating a temporary joint between the two parts that will keep them locked together. When sticky off becomes true, the joint is deleted and the stickiness goes away. We can use this to simulate the arm picking up items. One thing to note is that this new feature is not limited to this use. You can use it anywhere you want parts to stick together. For example, say you had a gecko pads for the feet of your robot. You could use this feature to simulate the robot walking on walls or upside down. The left contact sensor already has the sticky part flag set to true. So now we just need to use it. However, before we do that, we should add a circuit to stop the gripper arms from grabbing onto the part too tightly. We should make it stop as soon as the contact sensor detects it has touched them. To do this, we'll add a new rigid body node to the network and connect it to the L grip pad. Connect it to the grip close neuron. Change the source data type to be contact count. Set the gain of the C parameter to be negative 10 nanoamps. So what this does is when a contact occurs, contact count will be 1, and it will inject negative 10 nanoamps into our target neuron, which is grip close, stopping it from closing. Now to test this out, let's change the grip close end time to be 3.5 seconds, which is way longer than it needs to actually grip onto the ball. Then let's take a look and rerun the simulation. Yeah, and you can see, if you noticed, how it gripped, it stopped, and then once it went up and it couldn't pick the ball up, it kept on going after that point. So we can tell that our grip stopping mechanism worked. Let's go ahead and change this back to what it was before. Now let's add the sticky control. Copy the grip on neuron and paste 2 new neurons into the network. Let's name them sticky on and sticky off. Then let's draw connections to the left grip pad. We'll use these neurons to control when to turn the stickiness on and off. To do this, we'll be using another new feature of AnimatLab, target adapter types. Previously in AnimatLab, you could select the source data type that you wanted. But targets always only had a single type that could be used. However, this was quite limiting. You can now have the ability to set a target data type as well. For the sticky on adapter, we want the target data type to be sticky on. And for the sticky off, we want it to be sticky off. We'll leave the gains at 1, their default value. Now, when we stimulate sticky on briefly, it will set the sticky on parameter for the contact sensor, which will form the temporary joint. The stickiness of the contact sensor will stay locked. So once you stimulate sticky on, it will stay locked until we stimulate sticky off. So let's go ahead and add a tonic current stimulus to the sticky on neuron. And we'll set it to start just as the gripper should be closing on the object. Then add another one to sticky off. And we'll set it to be the time just as we start to open the gripper. Now let's run the simulation again. Hey, there we go. We got it. It picked the ball up, moved it over, and then dropped it into our container. So now that we have a very simple control system set up for the motors in the simulation, we can start the fun stuff. In the next tutorial, I will show you how to connect this simulation up to control our real robot arm.